Hello, everybody. How you doing today? This will be the nice little video for us for this summer test. I hope you have enjoyed this and are learning a little bit about energy. I hope I didn't bore you too much or anything like that. And today we're going to finish up. We're going to talk about hydrogen. And hydrogen, if I can figure out how to start this thing, is one of my favorite topics because I really believe that the hydrogen economy, and I'll say the hydrogen economy a lot throughout this, um, is one of our best chances out there to really revolutionize how we deal with energy. It's just that the conversion is going to take a long time and a long process. Um, so in this lecture, we're going to talk about the hydrogen vision of the future. We'll talk about some hydrogen systems, how we produce hydrogen, storing and the transportation of hydrogen. We'll talk about some of the problems and some of the promise, and we'll summarize everything up at the very end for you. Okay, so just like biofuels and fossil fuels and all this stuff, we've been using hydrogen for a long, long time and trying to deal with it or capture it for a while. And this guy in 1870 talked about this, and he says, I believe that the water will one day be employed as a fuel, that hydrogen and oxygen will constitute it, used singly or together. All right, so we can either take that oxygen and make ourselves fuel out of that, or that hydrogen and make a fuel out of that. Will furnish an exhaustible source of heat and light. This is exhaustible, okay, uh, of any intensity of which coal is not capable. So what I like about this, when he says it's an inexhaustible source of heat and light, hydrogen is an element, all right? So when we think about the second law of thermodynamics, first and second law of thermodynamics, we only break it down to certain elements, right? Things, the periodic chart. We get hydrogen, and that hydrogen is not going anywhere. Okay, so it really is reusable and renewable, and it is the most abundant element in the universe. All right, so if we can figure out how to really capture this hydrogen and then utilize it in an efficient way, we would have an exhaustible source of heat and light. All right, that coal could never even produce. Okay, because we keep on reusing and using it. If you think about the sun too, that is the helium and hydrogen molecules being squeezed together to make that photon under that great gravity, but we just can't reproduce that gravity to make that. All right. I believe that when the deposits of coal all exhaust, we shall heat and warm ourselves with water. Water will be the coal of the future. All right, and this guy was thinking as water, but we got to take that water. We'll talk about this again later on. Is how we get that hydrogen. We have to get it via the water. So this guy was talking about in 1870. Here we are, 2020, and we got a lot of good things going on. All right, so we're trying to do like what's called a hydrogen economy. All right. So a lot of we'll find out this in a little breakdown, but a lot of our hydrogen right now comes from natural gas. All right. And we separate that so we can burn it to make some electricity, but we get that hydrogen out and we can do the same thing. All right. It can also be hydrogen can also be used to help sequester the CO2 in the atmosphere as well. All right. But that extra hydrogen we get out of the natural gas and through the water and stuff can turn to do a ton of things. We could burn it to make some gas turbines, all right, to make that electricity, all right. We can also put it in our cars as a fuel, all right, and we can also use it to make electricity as a fuel cell. And I like this better than burning it, all right, because we don't have to start the plant up. We'll talk about this in a little bit, but we don't have to start this plant up. It really helps with the deck curve. That fuel cell can make that electricity lickety split. It doesn't need to be warmed up. And we talked about that deck curve with the solar and wind and how Germany's trying to carry it. It could actually flatten that duck curve out and have that backup source that we need real fast, right? Uh, Also, we can, believe it or not, fly some planes. You'll see one of the planes out there. I have a picture of it. It's not really that nice, all right? But these hydrogen pipelines can feed all these different people. We need a new hydrogen pipeline facility. Okay. Yes, we do have some natural gas pipelines and stuff like that, and they could be converted over, but we still need to have the central plant and then hook the central plant up to the grid there. All right, Hong Kong is actually doing this a lot. All right, I don't know if they're going to continue doing this because they're having some troubles in that community. But I know that China really wants to do some renewable energy stuff, so I don't think they're going to take this away. But the infrastructure is defined, developed, and delivered. All right, so they have a lot of hydrogen backup power electrical generators systems for a lot of the skyscrapers in there. They're using it for home fueling. They have this little box right here. You can actually plug in your water tap and make that hydrogen. All right, and go in there and fill up your home. All right. They have hydrogen residential storage units for some people in there. Hydrogen tanks on some of their buses. Okay. Community fueling infrastructures being built around Hong Kong. So if you want to see a nice case study and see how a city or even a nation, I guess Hong Kong is almost a nation, but still a city, is transferring over to a hydrogen economy. Hong Kong is definitely one of the first ones on the cutting edge of this. All right. Also, like I said, China. I just put this picture up here of these new buses that run on hydrogen. All right. And I like how they're set up because it's raised up so the cars can actually go underneath it. And they're not blocking any traffic whatsoever. And this is the on and off ports here. So the people get on the little bus, going down the highway and getting off the little bus and going to where they need to go. And notice these are raised up. So this hydrogen, right, for these new buses in China, it's not running on a hydrogen fuel tank. It's actually the hydrogen is creating the electricity to make these maglevs. All right, so you know about maglev fields, like on those roller coasters at Kennywood and stuff like that. This is all this is. It's one of these roller coasters, and that's done via electricity and doing the opposite. Instead of the magnets making the electricity is depolarizing those magnets, giving it north and south and moving it forward. Okay, but I like how this design is. Okay, that's why I wanted to throw that in there. And also, we need all these hydrogen fueling stations to be put around. Okay, and this is what one would typically look like. It's just a big tank of hydrogen. All right, and you just pull up and do the same thing with your gas tanks. All right, instead of having that liquid fuel go in there, you'll put the hydrogen in there. And when this is actually a little bit safer than liquid gasoline, believe it or not, because that liquid gasoline is a toxin and it gets on the ground and goes ahead and can seep into aquifers and all this other stuff when it's so stored underneath and things like that. It can leak and cause some environmental damage. But hydrogen, believe it or not, is a gas. So if it does leak, it's going to go straight up in the air and just go find some oxygen molecules and make some water. All right, it's not really going to harm you and explode. I mean, a lot of people get scared of explosion with hydrogen, but it's not really that possible, right? Because it's so diffused. All right. So the hydrogen production cycle. There's a couple of different ways we can do this to make hydrogen. All right. So we can use biological, we can use solar, wind, nuclear, fossil fuels. All right. To get that H2O or that hydrogen. Sometimes we take it out of the fossil fuels, and sometimes we do what's called electrolysis, which we'll talk about in a little bit, and we get that hydrogen and make it into that gas hydrate. All right, so we're just the H2. We can store that, and then later on convert it to what we need. All right, we can use it for the fuel cells in our cars. Okay, put that gas directly in our cars to run our fuel cells. Consumer electronics, we can make different plastics and things like that out of it, and also we can create electricity. So we can keep that lights going on, or heat, and burn it for heat generation. Okay. So hydrogen production into the hydrogen economy. All right, so the hydrogen economy is going to change for a lot of these different things. All of our packaging, our distribution, our storage, and our transfer really needs to be um, switched over from how we do this with fossil fuels, with coal and natural gas and oil, right? Because the distribution, although we'll have some pipelines and stuff like that, we're going to have to package it. We're going to have to compress it or liquefy it or put it in what's called a hydrate. That's more of a solid state form, all right? And this is really hard to do. But the two best are compression and liquefaction. That way we can take it down the pipelines, the roads, the rails, or the ships. All right, and these pipelines, you just can't convert from natural gas to hydrogen because the pipelines have to have different specifications to keep the stuff in there. All right, and then the storage is also going to have to be pressurized or cryogenic, freeze it down into a liquid form. All right, and we have to change it from that gas, collect it, compress it, and send it on out. So you can see that the changing over to the hydrogen economy, there's a lot of engineering problems that we have to overcome, but we can do it. I know we can build that kind of new kind of grid, I guess I should say. All right, and then after it's all done, we can switch it back into hydrogen, and we can burn it, or we can run it through a fuel cell to give us some electricity, whichever one we want to do. So the supply chain comes from all different stuff. So we have the feedstock right here, all right? And we have to send that out to a new H2 manufacturer. We'll talk about some of the different feedstocks and these manufacturers on the next slide, all right? And then we got to come up with a new retailing area, all right? And both these places need the storage, right? Okay, and then with a new H2 wholesale market supply needs to be made up. So instead of going to the like the play on Wall Street and there's future markets for oil and natural gas, no future markets for coal. But I envision someday that we'll have to have a futures market for H2 for hydrogen so that they can sell those futures so these manufacturers and retailers and stuff can plan their pricing for this stuff. All right. And then, of course, we've got to get it out to the consumers and then the equipment and manufacturing. All right. And all this is going to take new regulations as well. So as we set up each one of these little things, the Uncle Sam's going to have to step in and make sure things are safe and well maintained. Okay. So you can see already how a new infrastructure is needed for this hydrogen economy. And that's one of the things with those people in this podcast talked about how they want the cars all driven on hydrogen for the electricity fuel cell cars. But we really don't have the infrastructure set up. And it's going to take a long, long time. And to get that done by 2035 will be almost impossible. All right, it's kind of pie in the sky. And some of this technology still is not actually done and proven to be viable. Okay, but there's a lot of advantages to a hydrogen economy. Okay, first, the waste product of burning H2 is water. So we set that H2 out there, that hydrogen out into the atmosphere, collects with an oxygen molecule, and becomes water. And that's it. That's our waste stream from H2. All right. So that eliminates the use of fossil fuel pollution. Okay. If we're using the H2 to, convert that into energy, we have no fossil fuel pollution. We also have no greenhouses. It gets rid of our economic dependence on other foreign nations, all right, for our fuels. Like I said, we only have about 2% of the world's oil, so we're always going to need oil from either Canada, and Canada is a foreign nation. So, we don't really have that much. We might have enough coal to last forever, but definitely not enough natural gas, right? And distributed production, all right? So we can also produce this all over. Remember, I've said a couple times during this class that the ecological economists like to say the macro is only as good as the micro. We could actually have a lot of different micro production facilities because it's just taking water and running some electricity through that, and we get the H2 on one side and the oxygen on the other side. It depends on how we make that electricity, of course, but we can have all these little kind of production facilities and have them all tied in together. And if one goes down, the other one can maybe step up, and we won't miss it because all those different nodes we look in backing each system up. Okay, but there are some issues. All right. So hydrogen really is not widely available on planet Earth. All right, it's always locked up in something. Okay, in our water or in our hydrates in the ocean. Okay, but usually chemically combined in water and fossil fuels, they can be separated. All right, so like I said, our majority, as you'll find out, a majority of our hydrogen comes from fossil fuels, from separating that hydrogen from the fossil fuels, and we never really used it. What we would do is we would get rid of it because we get a bigger bang for our buck when we burn it. All right. But we can definitely separate it. This becomes costly though, okay? Um, and we need to be careful. All right. So fossil fuel sources contribute to the pollution. So if we're trying to electrolyze this water to get the hydrogen out using fossil fuel source, there is no carbon plus. We're just not fighting climate change. We might as well just burned the fossil fuels and got electricity straight from it and used it in our houses. All right, so there really is no advantage of trying to get electro water, hydrogen from fossil fuels. Electrolysis costs produce amount of energy. So, to get this electrolysis going, which we'll talk about here in a little bit, to separate that hydrogen from that oxygen molecule, cost is a lot of money. It's a lot of energy to be put into that. Okay, and we got to make sure that the energy that we put into that is actually, clean, I should say. And there are some technological questions. All right. So where does the hydrogen come from when we get it? How is it transported? How is it distributed? And how is it going to be stored? And all these answers have to be answered for the hydrogen economy to take place. And we're starting to form some of those ideas right now. We can see that happening in Hong Kong, as a matter of fact. So how is hydrogen produced? Most of our hydrogen is produced from reforming fossil fuels. So we heat the hydrocarbons with steam, and that produces H2 and CO. All right, and we could take that H2 and we could sell it on the open market nowadays. Okay, we also do that electrolysis of water, where we use electricity just to split the water of the oxygen into hydrogen, oxygen O2 into the H2. Okay. And we also have what's called high temperature electrolysis. And that's what they talk about a lot in that one paper for Solutions Project. All right, so this is still experimental. All right, and if it really pans out, it will be a good bang for our buck. But yet we still don't have this en masse. All right, and we also have something called the biological process. Okay, so believe it or not, Mother Nature has been splitting the hydrogen and oxygen molecule for a long, long time. All right. So we are experimenting with this in labs to see if we can actually build this up and make it a bigger scale. All right, so let's go over these a little bit more. First, let's do the breakdown. All right, so 48% of all of our hydrogen that we use currently comes from natural gas. So we clean it up and get rid of that hydrogen because we want a bigger bang for our buck, and also for the oil too. We get rid of that in our oil, so we can separate these already from all of our fossil fuels. So the majority of our hydrogen that we get is fossil fuel made, and only 4% is electrolysis. And we need to have this all 100% because we don't want to be using all these fossil fuels. Okay, so that's what we're trying to ramp up in the world of hydrogen today, is trying to use water, electricity, running electricity through water to get it. Okay, and you can see the global production about 50 million tons per year. It's growing about 10% per year. The U.S. production of hydrogen is about 11 million tons per year. So it's still, all things considered, a small marketplace, and it really needs to be grow if it's going to catch on here. But the main way we get it, or want to get it in the future, is through a process of electrolysis. All right, and that's just basically putting electricity. You can see this. You can do this a little test at your own home. All right, you can set up a little 6-volt battery. Okay, and set in a cathode and an iode up there, and connect the electricity, and that will send hydrogen up one test tube and oxygen up another test tube for you. All right, up these 10 strips. Okay, and it really is a simple process. But let's watch this video here. This is a good video of electrolysis process and what we're trying to do with it. I already have it fired up.
Photovoltaic panels are an ever-advancing technology used throughout the world, which creates electricity from the sun. However, storing the electricity for later use is the biggest challenge.
And that's what we want to try to do. Instead of using the batteries, we want to try to get into
batteries for energy
hydrogen
storage,
power,
which are expensive, difficult to dispose of in a safe manner, and have to be replaced frequently. But now there are other viable technologies and systems for storing energy, even for the average homeowner. The system we want to introduce to you is hydrogen energy storage. Hydrogen energy storage has several important advantages over battery systems. The underlying technology that makes this possible is hydrogen electrolysis. You may remember your high school chemistry teacher using low voltages to create reactions in various solutions. This is the electrolytic process and can be used to split water into hydrogen and oxygen. The machine that does this is a hydrogen electrolyzer. We use hydrogen electrolysis to convert electrical energy and store it into tanks in the form of hydrogen, which can be transformed later back into electricity. Hydrogen electrolysis from water is usually undertaken with liquid alkaline or
I think I hear
electrolyte
someone
membrane
talking in the background.
electrolyzers. The alkaline electrolyzer works by immersing 2 electrodes in a liquid electrolyte. When a voltage is applied, the product gases are released, in this case oxygen and hydrogen. However, it does pose some problems. It is unable to make efficient use of intermittent power supplies, meaning it's incompatible with renewables. It also compromises efficiency during storage. To store enough hydrogen for regular use, you would need either a giant tank or an additional compressor. The PEM electrolyzer overcomes some of these issues by using a solid polymer electrolyte, which is the membrane responsible for the conduction of protons, the separation of hydrogen and oxygen, and the electrical insulation of the electrodes. It's able to make use of the fluctuating power supply from renewables and results in pure hydrogen due to the solid structure of the electrolyte. It is easy and more efficient. However, it has a prohibitively high cost due to its required use of gold, iridium and platinum.
Platinum is the most expensive metal out there.
Fortunately, a new type of electrolyzer, the anion exchange membrane or AEM electrolyzer, provides a solution to all of these problems. It uses an alkaline solid polymeric membrane, eliminating the need for rare and expensive noble metal catalysts. The AEM electrolyzer is a simpler and more efficient system that produces directly compressed hydrogen. It's the key technology that enables lower overall costs. The AEM electrolyzer combines the benefits of the PEM electrolyzer with the cost of an alkaline system. It's an important breakthrough which will enable the economical adoption of hydrogen energy storage systems all over the world. Please contact us for more information on this groundbreaking technology and how it can benefit you.
So that's a little overview of the electrolysis process that is going on in the world today. Let me get that back up. Hold on a second. I don't want the video to keep on going. Alright, so that's the overview of the electrolysis process. And it is, the best way to do our, get our electricity, okay? But however, we want to try to do this with using renewable energies, right? And even the nuclear power plants that we have out there. All right, because if we just use the fossil fuels, we're not really gaining anything when we're producing this. There's no real offset, right? And we want to use it for the storage. So instead of using the battery arrays for the storage, we use the hydrogen and compress it and use that. Okay. There's also what's called biological H2 creation. So nature has a very simple method of splitting water. They've been doing it for years. And scientists are now working to mimic these processes in the lab, and then hopefully commercially. So what we do is take some plants that is all grown and we chop them up, all right, just the leftover biomass, and we throw it in there, and some bacteria actually consume, releasing the CO2 platinum, and then we have the divider over here on the other side, so the protons, just like in that one fuel cell. All right, anode and the cathode, and we just take that hydrogen's released and back in there. All right, and this is a very, very natural way of getting hydrogen, but very expensive. And to do this on a large scale right now has not really been proven viable. We do have some pretty big biodigesters out there that are trying to do this, but hopefully, they'll make an impact, but they really haven't come to fruition at all yet. All right. Hydrogen also needs to be stored. That's one of the main purposes of it, is that if we can break that hydrogen off that water molecule and store it, we'll be set, right? But it has some major difficulties. All right, H2 has low energy density per volume, so we require a large tank to store if we were just going to store it alone. All right, in its natural gaseous forms. Right. So what we have to do is compress it, just like we do with the natural gas when we try to send it over to Europe or something like that, or even down some of our pipelines. All right. And that's going to require some heavy, strong storage tanks, right? Like I said, each pipeline, we just can't put this in a natural gas pipeline and send it down the ways, because each one of these gases has a different intensity to, compression it needs. So those pipelines really have to be different than your natural gas pipelines. It can be liquefied to reduce volume. And this is called cryogenics, but it has to be frozen at negative 423 degrees Fahrenheit. So that takes some heavy energy to make that happen. And those tanks also have to have a heavy insulation, and it's very expensive to keep these cryogenic tanks at the required temperature. So both compression and liquefaction require a lot of energy. So we got to do that total throughput. How much energy does it take to create that hydrogen? Then how much energy does it take to keep it in the cryogenic state? And then how much energy does it take to transform that from the cryogenic state to the efficiency of what we're finally going to use it for, and create that water molecule at the very end. Okay? And that's one of the biggest reasons why we're having trouble switching over to the hydrogen economy. Ammonia storage too. H2 can be stored as ammonia and H3. So we can, change it over and then have to switch it back over to get that hydrogen afterwards, right? Exceptionally high hydrogen density. Okay, and when we do this, ammonia is very common chemical. It has a large infrastructure already exists for this. It's easily formed to produce hydrogen with no harmful waste. So once we add this into the ammonia state, it's easy to get that hydrogen back out. All right, but ammonia production is energy intensive. All right, and all right, so it's going to take a lot of energy to make the ammonia. Ammonia, of course, is a toxic gas as well. So we're taking it from a non-toxic hydrogen state into a very highly toxic state of ammonia. All right, but switching that back out is not hard at all, and it is actually better than compressing or liquefying the hydrogen. Okay, and there's also what's called metal hydrate storage. All right. So metal hydrates can carry hydrogen. So we can use boron, lithium, sodium, all right, and add that molecule back in to create this boron, lithium, and sodium. And it's good energy density, but worse than gas. Okay. The volumes are much larger than gasoline, 3 times more volume, to 4 times more heavier than gasoline. So if we switch this over to these metal hydrates, we will be dealing with even um, a bigger mass. All right, so we have to have bigger tanks, um, bigger storage tanks, bigger pipelines, and bigger everything if we're going to make it into this metal hydrate storage units. All right. And hydrates can react very violently with water. The leading contenders right now out there that we're trying to work with, and this is all part of the one of the reasons why like those guys don't like the solutions projects answer, and I don't like it either because I think we just go to algae. But the leading contenders are sodium and lithium and ammonia, boron. But it's very expensive to be able to do this, and the technology still really isn't there to make it happen. But scientists are still working on it, and I say keep on going for it. Okay, I have no problems with them still going for it. All right, so to store and transport the gas, it's going to be really bulky. And compressing H2 requires a lot of energy. All right, but compressed H2 has far less energy than the same volumes of gasoline. All right, so there's always that trade-off that we have to look for. And as a solid, the sodium and calcium and lithium and sodium hydrates really haven't been brought to fruition, but you can see it's going to be a big, huge tanks to be able to do that. All right. So there's a lot of different, just like we do with the natural gas, but we have to do that break even point and see, the total throughput and see how much energy we are like really getting from this. But I do like the hydrogen powered cars, right? Because it's basically not hydrogen powered; they're actually electrical powered. Okay, we're just running through a fuel cell. So you got your hydrogen in here, and then your fuel cell economy up here in the inside the car. All right, and I really like it. I like it. It's called what's called a skateboard car. All right, so the whole shell right here is now this is the newer technology than this old Ford. Uh, Picture. All right, but this is what it basically looks like, and you can drop any shell you want on this skateboard. All right, so say I got to run the kids to football, I can just put the minivan shell on here, and then when I come home and I got a hot date with a lady, I can take the minivan shell off and put on the sports car. All right, and I'm out of there. All right, and then when I want to go to school, I can put in my little family sedan, a little two-seater for me or something. Okay, so it's very versatile, right, for these cars, and that's why I like it. But once again, we got to build the whole infrastructure to be able to fill up these gas tanks, these skateboards. Okay. Hydrogen powered trucks are also on the go. All right, this gives us a little bit more infrastructure, or a little, the trucks are a little bit bigger to run them on, and we can store these tanks, the hydrogen, a little bit better on these, all the way through on the sides. Right, bigger storage units, and they're really starting to catch on. But once again, we still need to have the hydrogen infrastructure to be able to fill up these trucks on the go. And believe it or not, we do have hydrogen planes, hydrogen-powered passenger aircrafts with cryogenic tanks And you can see how crazy this is. All right. Hydrogen fuel requires about 4 times the volume of a standard jet fuel. So we have to add all this stuff on top. And you could, kind of guess that that's not going to be too economically feasible for the airlines to start building these kind of planes and run long distances on. They still got to get first. They got to get a couple more passengers to begin with. All right, so these planes aren't going to go anywhere, but they do exist. All right, and they were right. Solution Project says it can be done. It can be done. It's just going to be too expensive. Well, some of this is not. Well, these work. All right, that's for sure. They work. It's just going to be way too expensive. All right, and we also have hydrogen powered rockets. Believe it or not, the space shuttle, that big explosion you see, that fuel tank, that's hydrogen. That is not gasoline or diesel fuel or anything. That's actually hydrogen that's running it. All right, and we're getting a lot better running. I mean, a lot of the hydrogen technology comes from NASA and how they were able to do that with the space shuttle and everything else. Okay, and you can see the implications of hydrogen transport. So this is just the breakdown of the typical 18-wheeler and sedan compared to the 18-wheeler truck with hydrogen and the sedan with hydrogen. Okay. So you can see the typical 18-wheel diesel truck, the weight of fuel is 1,175 pounds, but the truck converted with ice hydrogen, so that will be the cryogenic, is only 313 pounds, so a lot lighter. All right. The sedan hydrogen fuel cell, right, is 14 pounds, and 118 for the gasoline. Right. The weight of the tank, though, is a little bit different. Right. So to keep this hydrogen in this ice form in the cryogenic state, that's going to weigh 31,000 pounds. All right, just to keep this 313. So the break off is not as efficient as people think, right? Weight of a carbon fiber tank is still 7,000 pounds. All right, but the distance you can go to, all right, the volume of the contents, all right. So you have 22 feet compared to 67 feet. All right, for the sedan, 22.2 feet, and 4. All right, so you get a little bit more volume as well on these tanks. All right, from 2 feet cubed to 9 feet cubed. All right, from 24 to 157. So there's some break even. Some values you got to think of when we switch over. Is this extra weight worth this extra distance? Okay. So in conclusion, the hydrogen economy is very promising in my book. But a new infrastructure that needs built is a huge barrier of entry for this. Okay, that is one of the hardest things for us right there. All right, hydrogen is as for backup storage on the grid is more promising than batteries. Okay, so that's definitely a better way to go. I think it will help with the duck curve. All right, a lot. And also the cost decrease and the efficiencies increase. I'm sure that someday hydrogen economy will definitely catch on. So I am hoping that that is going to happen here in the near future. Okay, so that is it with hydrogen economy. Remember, your papers are due on Sunday, and so is your presentation. And next week we'll have a final, and you got to watch everybody else's presentation and send in a little grade on that one. All right. So if you guys have any questions about your paper or presentation or anything like that, please just send me an email, and I will try to answer it to the best of my ability. All right. So everybody have a good evening, and we will be talking to you soon. I guess maybe, or maybe not. Okay. All right. So we'll see you later. Bye bye.